if we have a vector field F and a curve C, then we can integrate F over the curve C. So let's suppose that C, so to define this, we'll suppose that C has a parameterization given by a function r of t for t between a and b. And as usual, we'll assume that C is smooth. So r prime of t is defined and it's never equal to 0. Okay, so in this context, recall we defined we have the unit tangent vector. So there's two ways of defining this. So one is we take, this is sort of from the definition, is we take the tangent vector, or the velocity vector, and we just normalize it. So now it has norm 1. But this is also the tangent vector in the arc length parameterization. So our integral for vector fields will extract, so we want to extract the component of f along the tangent vector at each point. So our definition the integral of f over c is integral over c f dot t ds. And so this is equivalently the component of, like, the magnitude of the projection of f along t, since t is a unit vector. But then we can expand this out. So this is integral f dot dr by ds ds. Again, the arc length parameterization is very hard to find in general, but we can equivalently write this as f as an integral over in the t variable. So dr by dt dt. So yeah, and then taking this dot product, and we also write that as integral c f dot dr. So this expression, like dot differential of a vector, might look sort of strange, but this is what we mean by, so dr is dr by dt, and then that's what we, when we say the dot product, we mean like dot with this part of it. So these are all just several different ways of writing the same expression. So some examples of this are, some applications of this is if f represents, I should say represents a force field, so like gravitational force or magnetic force or what have you, then this integral is the work. This is calculating the work done by F in moving an object along C. So work is equal to F dot T ds. Now this is sort of for, I guess, a definition kind of for any random kind of curve. There's another concept that is mathematically equivalent in that we'll just be taking one of these line integrals, but physically it's slightly different. So if F is the velocity field, well, I mean, they're physically different in that they have different units. So the velocity field of a fluid, like water or or wind or whatever, then the integral is what's called the circulation of F around C. Or sorry, I should say flow is the flow of F along C. So flow is integral F. And again, this is just another notation for writing. This is the same as writing F dot T ds. And then if C is a loop, meaning it starts and ends at the same point, then we also call this what I said the first time, then we also call this circulation. So as the name suggests, this is measuring the tendency of, if you had a bunch of water, so if your curve was, if you took your curve to be a circle, this would be measuring how much and then if your fluid was, your force field was this, then this would be calculating that this fluid is circulating around this curve. So I'll do some examples in the videos below. Here I just wanted to get through discuss the concept and sort of the many different ways of phrasing this. In particular, we often want to, just as it's very useful to decompose a force into its components, let me just write N, J, and P, K. These are still functions of X, Y, and Z. I'm just abbreviating. It's also useful to break up the line integral into the contributions from these separate pieces. An example of this would be if we might only care about the vertical direction for gravity, or if we have sort of water that's flowing in, I don't know, some sort of pattern, against a dam, we might only care about the work that's being done in the direction of the dam. So we'll define, so if M, let me say if f x, yeah, I'll just do a new slide. So if f of x, y, z is a real valued function, as opposed to a vector valued function, then we define the integral of f dx over c to mean integral of f x, y, z, I. So we turn this into a vector field just by putting it as the coefficient of I. And then we take this line integral times t ds. And then similarly, we define the integral of f dy over this curve to mean, turn this into the vector field describing the coefficient of j, and then f dz is k, and then that dot t ds. So with this notation, okay, so with this notation, let's say f is a general vector field, so m mi plus nj plus pk, where again m, n, and p aren't constants, they're functions of x, y, z, just omitting that to save space, then from these definitions, maybe we'll just erase one. You can remember how it goes from the other. We get that the integral over c of f dot t ds, this is integral c m dx plus integral c n dy plus integral c p dz. And this is just using, this follows from the rule for dot products that u plus v dot w is u dot w plus v dot w. And then this is also written just integral c m dx plus n dy plus p dz. All right, so let me summarize. We've sort of seen a whole bunch of different ways to say the same thing. So yeah, let f be mi plus nj plus pk, c parameterized by r of t for a between t and b. Then we can write this integral f dot t ds. You can write this as f dot dr. Explicitly, this is the integral from a to b of f dot r prime of t dt. If we write r of, let's say r of t is fi, so f of ti plus g of t j plus k of t, so non-vector k of t times vector k, then we can also write this as integral ab m dx plus n dy plus p dz, which again explicitly means integral a to b m g prime of t plus n h prime of t plus p k prime of t, and then all of that dt. So maybe some names for these different forms. So this is sort of vector. There's a vector differential form. This is parametric vector evaluation. This one is a scalar differential form. And this last one is a scalar, or a parametric scalar. So, of course, to calculate one of these, you'll use this, but both notationally and conceptually, these are a bit more compact.